morning, friends. Today we will discuss about turning moment drawing. Basically, uh, now we will discuss about turning moment drawing for single cylinder double acting steam engines. Basically, in both strokes, during upward stroke and downward stroke, steam does a work on piston. So both the strokes will get a work on crank. So there will be work, we'll get positive work in both the strokes. So basically, turning moment drawing also referred to as crank effect drawing, because it is how much effect that the crank makes in each angle that is represented. So it is also called as crank effect drawing. So this is a graphical representation. This turning moment drawing is a graphical representation of turning moment. There is a torque at various crank angle. That is this one. This graph, I am taking torque, that is turning moment, in y-axis, and crank angle in x-axis. So in steam engine, first stroke, maybe steam comes in and the work is on the crank, so first stroke is positive, and in the second stroke, while coming back from inner dead center to top dead center, the steam is again making an work on crank. So that cycle is also in a like positive work. So what we study is here maximum turning moment got on here, and this is a mean torque. Mean torque, which is basically means as the minimum torque required to start rotate the flywheel. So till here we are getting work only how much needed to start rotate the flywheel. So after this only it is a useful work, that is a acceleration work. That means T minus T mean is an acceleration. If this is positive, we are getting acceleration. If this value is a negative, we are deceleration. That is retardation also. Retardation. So from previous classes we have been taught for a steam engine that torque is, turning moment is force exerted by the piston into radius of the crank, and angle where the crank angle is from inner dead center, theta is, and n is the ratio between crank length and crank radius, connecting rod length and crank radius. That is the ratio between them is n. So if we apply this, we will get the torque at each angle, at various angle. So basically we will plot out the result from this to this graph. For steam engine it looks similar to this, and here we know from starting we are getting the steam work done on crank, but till point B, that means some angle P, we are not getting any work that is capable of start rotating the crank. From point B onwards, the turning torque is more than needed than mean torque, that is it can start rotate the flywheel from here. This area is really huge compared to this one. Maybe if the flywheel mass is heavy, then this area is also will be heavy. And we all know work is here is T into theta. So this is the work needed to start working in this positive work needed. And here there are, from this drawing, when theta is equal to 0, we can say that there is nothing, because sine 0 is 0 and everything is 0. And if the theta is 90 degree, that means if this IDC to 90 degree, it has maximum torque is there in the output, and again in 180 degrees the torque reduces to 0, then goes up and goes down. This is for a double acting steam engine, single cylinder. Please note it, because every engine has its own graph. This is a schematic representation for a double acting single cylinder. So other things I want to clarify here is mainly the mean torque. We will study only the mean torque, but most of them doesn't mean what it exactly means. It is a mean resisting torque, the minimum that average resisting torque that a flywheel can. This is average torque needed to rotate the flywheel, start to rotate the flywheel. That's the mean torque. And other things can be